Our task here is to write the major organic product for each one of these reactions or reaction sequences. And in this question, what we want to ask ourselves is what adds? Where does it go? In other words, are we dealing with an initial group on the benzene ring that's an ortho-para director or a meta-director? And are there any issues? Is there an existing group on the benzene ring that's going to prevent anything from reacting? Is it going to blow up? Is it going to be overly reactive? Those sorts of things. So, starting with the first one here, if we look at the first set of reagents, what's going to add here is chlorine, right? And let's not worry about what happens next until we get there. And then if we look at our existing group, what we have here is a meta-director. So we're going to put a chlorine on the meta position, and there really aren't any issues here. And put a chlorine on the meta position. And then when we add the subsequent reagent, what's going to happen here is that that's simply going to reduce the carbonyl, and so our end product, kind of running into the blue highlighting there, is going to be this species, and for greater sanity, we'll put a cloud or a box or something around it. All right, so that's number one. Number two, we have this combination of reagents, and what that's going to do is add an alkyl group. And the existing group that we have on this is an ortho-para director. We really don't need to worry about how strongly activating it is. We just need to worry that it is an ortho-para director. And so we're going to stick that alkyl group in the ortho and or para position. And there aren't any issues here. This particular alkyl group is not one that's going to rearrange. In general, with an ortho-para ratio, unless the existing group is methyl, in other words, unless you started with toluene, you're always going to get, for steric reasons, more para than ortho. And so what you want to do in a scenario like this is either write just the para product, because that really is the major product, or you could write both products, or in the interest of time and space, you could just write this as some ortho. All right, number three, getting a little bit trickier because now we have two different rings. And so we have this ring, which is activated, and then we have the ring on the other side, which is deactivated. So what's going to happen here is that this ring on the left is going to be the more reactive ring, and so that's what's going to react. As far as what's going to get added, this is going to add bromine, and there aren't any particular issues. So again, we react this ring, we don't react that ring. And so when we write the product, I'm just going to try to move it so that we have a little bit of room here. Again, this is an ortho-para director. We're going to get more para than we are ortho. So if we draw this, and we'll put the bromine on there. And again, we can put a box around our major product, which I forgot to do on the second one. Oops, that's not what I wanted. Then number 4, now we've amped things up a little bit because we have 2 groups on the benzene ring. We have this tert-butyl group and this nitro group. And what's going to get added here is a nitro group. So the nitro group is going to get added. And as far as where it's going to get added, it's not going to go here. You never put the incoming electrophile between 2 groups that are meta to each other. So that one's out. And in a scenario like this, the more strongly activating or less deactivating group always wins. And so this group, probably at this point better to actually highlight it in some sort of a color. So this group is an ortho-para director, and that's a more strongly activating group than a deactivating group. And so again, our options would be to put the incoming nitro group either here, not too likely with that bulky tert-butyl group. This would be the better choice. This is para to the bulky tert-butyl group. And yes, unfortunately, it's ortho to the quote-unquote meta director, but again, the tert-butyl group rules here. So if we write the first product that we get from this, and then we're going to put a second nitro group there. And then we can ask ourselves what happens when we add the iron and HCl and so on. And what that does is it reduces the nitro group. I probably should have specified excess. That would have been better. And so what that's going to do is then turn both of these nitro groups into NH2 groups. My hope is by making this a little larger, maybe I can make it a little neater. And the function of the sodium hydroxide is that when you initially reduce this in acid, that these 2 amine groups are protonated, and so the whole function of the sodium hydroxide is just to deprotonate those 2 groups. Example 5, now we have 3 groups on the benzene ring. And so looking at this, again, nothing is going to go here because that's in between 2 groups, and that's just sterically unlikely. What's going to add, by the way, is this acyl group. There aren't any issues. And so now we have a choice between putting the incoming group here, which is ortho to one and meta to the other strongly activating group, or we can put it here. Again, we're not going to put it there. And between these 2 positions, this is probably your better choice, at least electronically. And the reason I'm saying that is that this is ortho to the ortho-para director and para to the ortho-para director. And that's a better choice, probably, than putting it ortho to the ortho-para director and then meta to the other one. So in other words, electronically, these 2 positions are essentially tied because they're both ortho or para to one OH group and meta to the other one. And so we're going to use this alkyl group as a tiebreaker. Now, is it conceivable that there's some kind of a steric factor because these OH groups might be smaller than this propyl group? Maybe, but we're going to make an educated guess here that the major product is going to be the one where I did not plan very well, where this acyl group goes on the position that's ortho to the ortho-para director, para to the other ortho-para director. And so that would be our major product probably here. Would you also get some of the product where it added there? Sure. And I apologize for my clock, but I'm not going to stop this. Finally, let's take a look at this one. And this is a reaction that we normally do in Chem 24 in the lab. Since we're not really doing real labs and we weren't able to find a video of this, we're not actually doing this this spring quite this way, but I'll go ahead and do this example because I typically do. And I've specified a couple of interesting things here. First, we have excess of this alcohol. And secondly, we have a set of reagents that they talk about on the in the UCI lectures, but isn't specifically mentioned in David Klein's book. And what these reagents are going to do is, if we use some of our previous chemistry, we're going to protonate that alcohol, which turns it into a better leaving group, and then it's going to leave. And so what we have here is an alternate way of generating carbocation as opposed to using an alkyl halide and aluminum chloride. And in the lab, it's kind of easier to do. So that's one issue. So now we know what adds. And the excess just implies that we're going to add two of these. So in other words, we're going to add one tert-butyl group, and then we're going to add a second tert-butyl group. So if we look at the initial reactant, it doesn't matter whether you put the tert-butyl group at any of those positions because they're all equivalent. You know, think about NMR, all of those carbons or all of the hydrogens attached to those carbons would be equivalent. So let's go ahead and put the tert-butyl group wherever we feel like putting it, because again, it does not matter. I'll put it there. So now when we go to attach the second tert-butyl group, now we have more choices. So we could, in theory, put it there. Not very likely because it's between this really big tert-butyl group and another group, and we generally, even if we have petite groups that are meta, we don't put anything there. So that's out. And then we look at these two positions, and these two positions are the same with respect to the strongly activating groups. So this one is ortho to that methoxy and meta to the other methoxy. This one is ortho to that methoxy and meta to that methoxy. And so what we're going to have to do is use the alkyl group as a tiebreaker. And if we look at the alkyl group, this is going to be the better choice and probably give us the, well, it definitely gives us the major product because we've been doing this lab for years and years. The major product is going to be one where the second tert-butyl group goes here, and that's again because the tert-butyl group acts as a tiebreaker. If you draw the resonance contributors for the sigma complex that you get as an intermediate, it turns out that you're able to put, when you attack with the tert-butyl group here, there's a resonance contributor where you have a positive charge on this tertiary carbocation, whereas if you put the tert-butyl group here, that doesn't happen. Because when we attach the tert-butyl group here, a positive charge gets directed to this carbon, and that carbon. So drawing at last the final product. So we've got our one tert-butyl group here and our second tert-butyl group there. And so that's going to be our final product. And it's kind of interesting to see how symmetrical this particular compound is. And the way we discern that we got this product as opposed to the other one, we do two things. One is it turns out this is a solid product, whereas the other possibility where you would have put the tert-butyl group here is a liquid product because it's less symmetric and has weaker intermolecular forces. And then we also take an NMR of the compound, and the NMR of this compound has more symmetry, and consequently